Okay, so today, in the last couple of classes, we're going to talk about statistics. Trying to remember, what did we get to on Wednesday? But remember how far we got? I've got it. So we're looking at statistics here, talking about vocabulary. So statistics is almost like a second language. So we do have to clear up some of the words used first. The most important concept to get is something called a population. And a population is simply the group we want to learn about. Okay. Now, population, it could be people, it could be a group of people, it could be a group of parts, it could be in medical testing, it could be different medical treatments or medications. It can be a group of anything that we want to learn about. Often it is difficult to define the population. You know, for example, let's say we wanted to look at the next school board election. If we want to try to predict who's going to win the next school board election, it'd be real easy to say our population is the school board candidates. But that's not really true. That's not what's going to determine this result. What we really want to learn about is the behavior of the people who are going to vote. Who they vote for determines that election, not the well, the candidates have something to do with it, but you know what I mean. But it's difficult to define. We can't just say all voters because the ones who aren't going to vote in the election aren't going to change the result at all. So really what we're looking at is the voters who will vote. That's our population. Let's look at the medical testing. Now, again, it'd be really easy to look at it and say, hey, we want to learn about the medications themselves, which we do want to learn about them, but that's not what our population is. Our population is the patients being treated. Because what we're really measuring is the recovery or the reaction to the medication. So we want to learn about the medication, but what we're really, our population is the patients who are using that medication, what the reaction is to it. No, but you kind of got to understand them to make the conversation make much sense. Now, when we do a statistical study, we're usually asking a question. Kind of, yeah. Yeah, like for the election, the question I would ask if I called up a potential voter would be, first of all, I'd probably ask, do you plan on voting in the upcoming election? If they said no, well, that tells me they're not in the population. I'm not going to ask them. But the real question I'm asking is, if they're going to vote, is who do you plan on voting for? The answer to that question is the random variable. We're going to talk a lot more about the random variable in the second hour, because that is kind of the focus of our part of the course here is working with that random variable. But let's get back to our vocabulary for now. A parameter is describing that answer for the population. Now, again, we're not going to call every member of that population and ask them who they're going to vote for. It's not very practical. But if we waited until after the election and we said, hey, 57% of the people who voted for candidate A, that's a parameter. It describes the population in terms of that question we were going to ask. It answers that question for the whole population. if I tried to gather information from the whole population, it's called a census. The US government has a census coming up here in a little over a year and a half in 2020. Every 10 years, the US government tries to do a census. One of the reasons for that is that's how we determine population for districting and stuff like that for congressional districts. Trying to make sure every district is the same size, has the same number of people in it approximately. And that's whole part of that equal representation. If one district has a huge population growth and the district next door has a drop in population, technically you could claim that those people in the district that lost population are more represented than those that gained population because they have more people for one representative than the other group does. Now, the U.S., it's kind of a misnomer to call the census because they've never actually accomplished a census. A census does require you get information from every living person. You do that's a federal crime, right? Yeah. Yeah, it's like punishable up to like 2 years in prison. Have they ever sent somebody to your house to try to get the information? Okay. Yeah. Because they spend billions of dollars. And to be honest, I wish they would adjust how they do the census because it is very expensive. Yeah. Well, the first one should come in the mail. And yeah, if you don't get that one, then they actually come around to your house and leave it on your door. And then if you don't fill that one out and send it in, then they try to come to your house and sit down with you and interview you. So I mean, the people that are resistant, it could be 2 or 3 trips to your house. And those people aren't, I mean, it's not, they're making like $15 an hour they're paying them. So it's not terrible money. It's not great money, but yeah. Oh, sure. Yep. So let's talk about something called a sample. A sample is a smaller group selected from the population. Not necessarily, well, that is a possible subgroup, but not necessarily a sample. So we talked about that parameter describing the whole population. A statistic then describes the sample. It's the answer to that random question for the sample. So let's say we'll talk back to that school board election. Let's say you randomly select 200 potential voters, you call them up, and 60% say they're going to vote for candidate A. That's a statistic. It describes the sample. 57 actually voted for him at the election. That's the parameter. It describes the whole population. And of course, gathering information from a sample is called a survey. Sampling is really a huge issue in statistics. What we want is something called a representative sample. Representative sample means quite simply the sample statistics, if not equal to, really close to, population parameters. They're not going to be exactly equal, but we want to try to do whatever we can to limit the differences. Two things that we do. We select an adequate size sample. Let's say that I asked you guys to do a study to determine the proportion of the percentage of students at WITC that are satisfied with the degree program. And you go out in the hallway and you just grab the next two people you see and ask them if they're satisfied. And one says yes, one says no. And you say, well, 50-50, it's a 50-50 split between those who are satisfied and those who aren't. No, that's too small of a sample. If you asked 100 people and 50 of them said no and 50 of them said yes, then you can maybe say there's an even split. So you have to have an adequate size sample. Second is random selection. Random selection simply means every item in the population has equal chance. So let's say you go out in the hallway and survey the next 100 people you see. Is that random selection? It's kind of tricky. It's not, because students who don't have Monday classes have no chance of being in that sample. Students at other campuses have no chance of being in that sample. Yeah, that's called a convenience sample. You're taking information that's easy to get, it's convenient to get. And this is done a lot. Most of the statistics you see on the news and stuff are political statistics. If you want to look at like approval ratings for politicians and stuff like that. Mark Twain once said there are lies, there are damn lies, and then there's statistics. And there's a lot of truth to that comment. Political statistics are just nasty. To me, the biggest thing in statistics is ethics. And there are a lot of ethical gray areas. There's been a lot of money spent through the years on psychological effects of statistics, just the color print that you print surveys in and stuff like that, and this responses it elicits. But for example, if I wanted to find what proportion of the population supports a candidate coming up for the next presidential election, well, I could radically affect the results of my survey depending on how I choose my sample. For example, if I were to go stand outside a church on Sunday morning and survey people coming down the sidewalk, usually you would get, people with religious affiliations usually support one party over the other. So you would get definitely a skewed viewpoint. Or if you go stand outside a rally for a candidate and then interview people on their political views coming out, obviously there's going to be a tilted view there. So you have to be very careful. Every member, no matter what group they're in, has to be part of it. We're not going to talk any more about sample selection because that's not really the purpose of this course. I could go on for a couple hours on how to choose good samples and pitfalls and stuff like that, because there really are a lot of different things that can go wrong. But that's not really our purpose. Our purpose is to get on to that random variable. And remember, that random variable is the answer to that question being asked. That random variable falls into one of two main categories. Categorical or qualitative. Can't spell today. Categorical or qualitative is kind of what it sounds like. The answer to that question puts you into a category. What's your favorite color? Well, whatever color you pick puts you in the category of people that like that color. What candidate are you going to vote for? candidate A or candidate B? Well, again, it puts you into a category. Any yes or no questions put you into a category. The other side of it is numerical or quantitative, depending on which textbook you're looking at. So the answer to that question is a quantity or a number. Now these can take on two forms, discrete or continuous. Discrete means quite simply counted. How many cars do you own? How many classes are you taking? How many children do you have? That's something you can count. Continuous is measured. How tall are you? That's something you measure. How long does it take you to perform a task? That's something you measure. Now, one that always kind of falls into a gray area is money. Everybody says, well, you can calculate money down to the fraction of a penny. But yes, you can, but normally when you report it, it is common practice to report it near a penny, and you can count pennies. So money comes under discrete. A lot of people make the argument, well, time, you typically do time in seconds, you can count seconds. Yes, but you're only limited because that's what you desired around it to. You can measure time to 1,000th or 10,000th or millionth of a second. The size of the unit is only limited by the precision of the measuring device you're going to use to measure it. One of the technical definitions of continuous is that if you go down to a small enough measuring unit, you can always find a difference no matter how close two people are. There's always a difference, or no matter how close two items are, I should say, there's always a difference. Like height, no matter how close two people are in height, if you go down to a small enough fraction of an inch, you can find a difference in their height. Okay, so we need to talk a little bit about those random variables. The categorical. So categorical or qualitative. Let's say I ask the question, what is your favorite color? But I only give you three choices, red, blue, or green. So you respond. Did we do this example yet? I don't think we did we? So let's say we get responses red, blue, red, green, blue. What's that? Oh, hang on. Let's see, 1, 2, 3. So there we go. If you look at this list, there are 30 responses listed there. What color looks to be the most common to you? It's really tough, isn't it? Depends on. If you focus right here, what color looks to be the most common? Red. How about right here? Green. Over here? Blue. This is where that psychology comes into it again. The human mind has been shown, the average human mind can only really focus on between 7 and 13 things at once. So trying to take in a set of 30 is just too much. You're only going to really take in, your mind's only going to take in like 7 to 13 of them. So then the rest it just fills in, like you said. So You look here, you see a bunch of red, your mind is going to see the rest of the red, even whether they're there or not. Yep. So raw data like this, while necessary, is not really useful for interpreting. If I ask you a question out of it, it takes a long time to get an answer out of here. So we organize it in something called a frequency table. What a frequency table does is it lists, for categorical data especially, it lists what our category is, in this case color. And I am being very careful not to use red, blue, or green for any of the colors I write in here. Back to that psychological effect. Let's say blue is chosen way less than any of the others, but if I make the graph in blue, still people reading it are going to latch onto the blue, and they're going to walk away thinking blue was the most common color, even if the numbers clearly show it wasn't. The blue color itself sticks in their mind. So usually we have all the different categories listed, in this case the three colors, and on the other side we'll have their frequency. Now, to create these, I usually add a column in the middle. I should have warned you beforehand. I'm going to erase that frequency. I'm going to move it over. And I'm going to add a column in the middle called tally. Now, if I were actually presenting this graph, this middle column would not be here. I'm just putting it in here to help me create the rest of the table. So here's what I'm going to do. We have red, red, blue, red. Red, red, blue, red. Green, blue, green, green. Green, blue, green, green. Blue, red, blue, green. Blue, red, blue, green. Anybody would have guessed we would be that close at this point? Blue, blue, red. Blue, blue, red. Red, green, red, red. Blue, green, green, green. Red, green, blue, red. Blue, blue, green. What did we find out? Exactly the same amount. Anybody would have guessed they would all be exactly the same off of that? No. So you can see the raw data can be very deceiving. Putting in that frequency table is helpful. Now to go to the next step, I'm going to change those numbers a little bit because having them all equal 10 is not very interesting. Now again, if we were actually presenting the table, we would not have that tally column in there. So let's say out of that 30, 8 people chose red, 13 people chose blue, 9 people chose green. We'll make you happy. I take it blue's your favorite color? From there, we can break things down into, this is a table. We can break things down into graphs. Now this table only has the 3 categories, red, blue, and green. So it's relatively easy to look at that table and pick out the largest number or the smallest number, and so on. If there were like 7 or 8 categories, it'd be a little tougher to do that. So what we're really looking at doing the graph, the reason for the graph would be if we had multiple categories there, and it's hard to sort through them. The graph gives us a much quicker, almost picture-like representation. One of the graphs we're going to look at is called a bar graph. Now, a bar graph can be done one of 2 ways. Either you have the categories across the bottom and numbers up the side, or you have the categories on the side and numbers across the bottom. In statistics, we usually prefer to have the categories on the bottom. So we got red, blue, and green. Then up the side, we have to make sure we get numbered up to at least the largest number. So that's 13. Notice I don't have to label every little mark. In fact, I don't have to have a mark for every one if I don't want to. So red was 8, so there's a bar above the red, goes up to 8. Blue is 13, so above the blue we go up to 13. Green is 9, so you go up to 9. Now looking at the graph, if you're asked which one's the most common, it's very quick to pick out blue is the most common. Least common, you got to look for a second, but you can see red is the shortest. Now again, this is more useful if there's like 7 or 8 or more different colors, then you can very quickly find the biggest bar and shortest bar and stuff like that. But if I asked you how many were green, well, this one, the numbers are small enough, you could probably trace that over and get that it was exactly 9. But in many cases, if you have larger numbers, you can't get an exact number from it. One thing I would warn you of is this. Let's say I want to compare 3 companies. Company A, B, and C. Which company sold the most? B. How much bigger is B than C? Well, looking at the graph, you'd be tempted to say more than twice as big, wouldn't you? What do you notice here, though? What's that little symbol there mean? What it means is the numbers are cut off. It's not numbered from 0 all the way up. You can see we start at 200 there. So it's legitimate to do this so that you can see the difference between them. But it's deceiving. Again, that psychology thing comes into play. Because if we numbered from 0 all the way up, A would look something like this. B would look something like that. And C, there's barely any difference at all between them, is there? Very small difference. Here, it looks like there's a very big difference. Here, you can see they're really close. The problem is here, you can't really see what the difference is between them. So we focus in over here. Even here, you couldn't tell exactly where C is. Is that 202,000, 201.5? It's tough to get exact numbers off the graph. If you want exact numbers, that's where you go back to the table. That is, by the way, a very common practice to cut off the axis like that. From the ethics side of it, again, I stress, make sure it's obvious, make sure it's marked like I did, and make it obvious. Generally, rather than doing the bars like I did, what you would do is something like this. You'd have this mark on the axis. So you'd put a mark all the way across the graph so that you can see that those bars are cut off and they're only showing the top part of the bars. Generally, what I would do is I would say you put these 2 graphs side by side. Then you show something like this so that you can tell this is a blow up of just that top section of the graph so that people get an accurate picture. Now, again, if I'm company B and I want to convince investors that I'm doing better than my competition, which graph am I going to use? First one, yeah, because that looks way more impressive. Other things that are used, by the way, making the bar for our company wider than the others. Now, I exaggerated there by making it way wider. But that width, psychologically, your mind thinks in terms of areas. Even though it's only the height of that bar that matters, the fact that it's also wider makes your mind think it's really big compared to the others. There's all sorts of little psychological things that come into statistics. So back to our little frequency table here. We could also have a circle graph. A circle graph generally goes off of percents. So what we're going to find here is something called the relative frequency. Relative frequency requires us to first find the total. Add those all up, we've got 30. So then 8 over 30, each item then out of the total. 8 out of 30 is 26.67%. 13 out of 30 is 43.33%. 9 out of 30 is 30%. Now, years ago, if we were making a circle graph, we would then take each of these percents and say, okay, what percent of 360 degrees, or how many degrees is 30% of 360? That's 108 degrees. Then we take a protractor and measure out 108 degrees. We don't need to be that precise anymore. If we needed to be that precise, we've got computer programs that do that perfect for us. So for our purposes, all we're going to look at is this. Half a circle is what percent? 50%. A quarter circle is 25%. If I cut a quarter circle in half, that would be 12 and a half, right? Half of 25, right? And we can keep slicing if we wanted to, but let's look at this. We see here 26.67 is just a little bit more than 25%. That's red. 43 is a little bit less. That's about 6 less than 50. So that would be half of one of these quarter slices. One of those quarter slices is 6.25. So this down here is going to be the blue. What's left is the green. Now, something you'll notice, I was avoiding those colors. Doing that in blue, even though blue is actually the largest one, doing it in blue also draws that to your mind. If I'd have done it in green, even though blue is the bigger slice, your mind still takes away the green. You ever seen that psychological test where they tell you to name the color and they have, or they read the word and the words are colors, but the word green is printed in blue and the word red is printed in yellow or whatever. So you're going through, and the first time they ask you to read the word, then the second time through they ask you to name the color. And even though it says red, it's printed in blue. So you're supposed to say the color, but you say red because that's what the word says. Little things like that. It plays with your mind. And statistics, there's a lot of ways in statistics to do that. Okay, so that is the second type of graph. The textbook talks about pictographs. Pictographs are something you need to see because they are used a lot in the media, advertising, stuff like that. Either one, actually. So technically, it's the type of data being used. If it's categorical data, it's technically called a pie graph. If it's numerical data, it's technically called a circle graph, but they're the same thing. Pictographs can be very misleading. When you look at a pictograph, all I'm really going to say about pictographs is read them very carefully. Because it's just very easy to make them misleading. One of the most common things in a pictograph is use the 3D effect. Let's go back to that company A, B, C, and D, or ABC again. Which one's the biggest? C is. But if you read it, all that's really being read here is this front bar. Now notice I was careful, I made them all the same width. I didn't cheat on that, but I cheated on the depth. A really has a value of 4, B a value of 3. Now A looks like it's almost twice as big as B, doesn't it? Why does it appear that way? It's because of the depth. C has a value of 7, but it looks like it's way more than double A, doesn't it? Because again, that depth that's been added to it. That's one of the ways picture graphs are used to be very deceptive. So when you read picture graphs, always look for the numbers and put in the numbers and pay attention to that rather than the psychological effect of what you see. Okay, so we've looked at organizing data for what's called snapshot type data. So that's just taking, we have several different possibilities. So several possible answers to that random question. So we were able to display all the possible answers and their frequency. Now what I want to look at is something called time series data. Time series data, there is only one thing that we're looking at. We're not looking at different possibilities, we're looking at one possibility. And we want to know how it changes over time. So the other ones, we're looking at one single moment in time and what all the how many of the different possibilities were chosen. Here we're looking at only one thing, but at different points in time. Like for example, we might look at WITC tuition as it's changed through the years. Let's go from like 1995 to 2000, 2005, 2010 to 2015. Here I am going to cut off my axis just to make it easier. So let's say that in 1995, tuition was $99 per credit. In 2000, because of grants and stuff, it was $92 per credit. 2005, it jumped up to 110. 2010, it jumped up. Let's get in there. 2010, it jumped up to 148. 2015, it dropped to 144. So if we look at this, this is called a line graph. First of all, a lot of people want to take this first point and connect it down like that. Don't do it. That line does not exist. It's not real data. It was not $0 at some point here in the past. The strength of a line graph. If I asked you what periods was the cost of tuition fall, well, you pick it out real quickly. Right here, because the line's sloping down, and right here. If I asked you what period did the price increase the fastest, that would be right here, because the line is the steepest there. If I asked you what was the exact price in 2010, where's 2010? We trace it over. I can't tell for sure, can I? Because I know it's in the 140s, the 150, but I'm not totally sure. If I wanted that exact value, that's why I'd go back to a table. So the graph is easiest, any graph is easiest for showing largest and smallest and comparing two values. If you want exact values, that's a weakness in the graph. That's where you go back to the table. Okay, it is about time for our break. So let's go ahead and take our break, and we'll come back here in 10 minutes, and we will start talking about describing data, summarizing data with numbers rather than pictures. So then the second part we want to look at summarizing data numerically. And when we do that, we have to understand what we're looking at. And we're looking at here, we're looking at mostly numerical data. So that the answer to that question is going to be a number, whether it's discrete or continuous. And we're looking at data distribution. So in a data distribution, we might have all sorts of different values. Let's do another type of plot. Called a dot plot. And what we're going to look at here is scores on a test. And let's say we have a bunch of students who take a test and all of them score between 80 and 100. And so we look at the first student scored an 87. So I'm going to put a dot above 87 to indicate their score. The next student scored a 94, so I put a dot above the 94, a 91, maybe an 89, 83, another 87. So I stack the dots up like that to indicate that there's more than one there. And so I keep putting dots on here to represent the scores of my students. And as I keep stacking them up, I see a shape that develops here. And more dots I put on there, the more clear it becomes. If I draw a line through the top of each of those stacks of dots, I get a shape something like that. Many of us have probably heard this referred to as the bell curve because it looks kind of like a bell. The scientific term or the mathematical term for it is a normal curve. It deals with something called normal probabilities. And it's called that because in nature, that is the shape that most data normally takes. Like heights of people at a certain age will make that shape. Scores on a good test do take that shape. It's a normal distribution. Now, if I were describing that, I'm going to scroll down here just a bit. Let's say I have one curve that looks something like this. Some of the things I could do to describe that curve, well, this one I might say its center is at just below 90. Well, I might have another curve, looks something like this. How would I describe the difference between that blue curve and the green curve? Well, the center of the green curve looks to be closer to between 91 and 92. So they have different centers. So that is one of the things that can be used to describe that distribution is the center of the distribution. Next, I might have something that looks like this. How would I describe the difference between the red and the blue? Well, they have the same center, but the red is narrower, tighter, however you want to describe it. The blue is wider. That's referred to as spread, sometimes referred to as dispersion. The dots in that red curve are tighter together, less spread out. So numerically, we need to find ways to quantify both center and spread. So we're going to start out, I'm going to give you a set of numbers down here that we're going to work with. I'm going to do this. So I have these numbers. Get out of my way. Okay, so over here, let's put these numbers down. Trying to get fancy and I'm going to cause all sorts of problems. Let's put down the set of numbers. I'm going to do 8, 13, 11, 21, 13, and 27. And let's do 18 in there. So there's my set of numbers. So I have them over there where I can see them. So now let's do some work with those numbers. One of our first measures of center is something called the mean. The mean is what most of us have always referred to as the average. How do you average numbers together? Remember how if I asked you to average three numbers, what would you do? Yeah, add them up and divide by how many are there, right? We're going to define something. Remember we said n equals the size of the sample. So it's the number of items in the sample. So to find a mean, you add and divide by n. So here I would do 8 plus 13 is 21, plus 11 is 32, plus 21 is 53, plus 13 is 66, plus 27 is 93, plus 18 is 211. Over how many are there? 1, 2, 3, 4, 5, 6, 7. Over 7. So 211. No, not 211. It should be 111, right? 111 over 7. That divides to be 15.85714,286 approximately. We're going to go 15.86. We're going to round that. That's the mean for that set of numbers. Big question on finding the mean. Okay, let's look at the next one called the median. The median is defined to be the middle. To find the median, we first have to put the numbers in order. So there's actually a couple steps we're going to go through. Step one is to put in order. So for this set of numbers, the smallest one would be 8, then 11, 13, 18, I'm missing one. Oops, there's two 13s, that's why. 8, 11, 13, 13, 18, 21, and 27. Second step is going to be find the position of the median. To do that, I'm going to take n times 1/2. N was 7, right? So 7 times 1/2 is 13.5. Now, since n was odd, we have to round this up to the 4th position. So what does that mean? We go 1, 2, 3, 4. I'm going to keep going here. 5, 6, 7. The number in the 4th position is the median. So 13 is our median. Notice we had 15.86 was our mean. So those two are not real close together. What does that tell us? Well, if our data is perfectly normally distributed, those numbers should be the same. So that means this data is not perfectly normally distributed, which shouldn't be a shock. The further apart those two numbers are, the further from normal the data is. So that's saying that not only are these numbers not normally distributed, but they're probably not really even close to normally distributed. Now, I said that works if n is odd. What if n is even? How would we find that center? Well, I'm going to give you a totally different set of numbers here. I just took out one of the numbers there. Now, I put them in order for you already, so we see step one is done. To find the position of the median, what's n equal in this number, or this set? How many numbers are in that set? There's 6 of them. So that means it's 6 times 1/2, which is 3. Since n is even, that tells us it's between that one and the next. So that means it's between the third and the fourth number. So 1, 2, 3, 4, 5, 6. Third number is 13 and the fourth number is 18. How do we find what's between them? Well, we just add them together and divide by 2. 13 plus 18 is 31. Divided by 2 is 15.5. Third measure of center we're going to talk about is called the mode. The mode is simply the number that occurs most often. The mode in this set of numbers over here, the 13 is the only number that appears twice. That means my mode has to be 13. There's a lot of discussions on modes depending on which textbook you're using. And there's actually a lot of different schools of thought in statistics. And this is one of the places where that kind of comes into play. Some textbooks will tell you there's either one mode or there's no mode. Others will say you can have up to 2 modes. Others will say it depends on the size of the sample. If you have, more than a certain number of modes, you can have, or a certain number of items in the sample, you can have multiple modes. For this class, there's either one mode or there's no mode. Now, to be honest, the mode is not really useful for numerical data. The mode is usually the most useful for categorical data. The reason for that, you can't find a mean or a median for categorical data. What's the mean of the colors red, green, and blue? Not possible, is it? But you can find the mode. You can look and see which one occurred the most often. So that's really where the mode is used, is in the categorical data. There's another one called mid-range. The mid-range involves 2 numbers, the maximum and the minimum. The maximum is the largest number in the set. The minimum is the smallest number in the set. So here our maximum would be the 27. The minimum would be the 8. So we add those 2 together and we divide by 2. When you do this on your calculator, make sure you hit equals before you divide. 27 plus 8 is 35. Divide by 2 is 17.5. That's a very rough and quick estimate of center. I'll just be frank with you, it's not a very useful one, not terribly accurate because it is quick and rough. generally doesn't give you a great estimate. So it brings us down to the question of what is the best measure of center? We said the mode is really only good for categorical data. We said the range is quick and rough. So it comes down to the mean or the median. Between those two, which one would you say is the best? A lot of people would say the mean just because it's satisfying. You grab some numbers, you added them up, and you divide it, you crank through a calculation, right? But let's look at some examples of what happens. The example I love to use is 1983. University of Virginia. Advertised that the average starting salary for their BS in marketing that year was just over $78,000 a year. Now that sounds pretty good, doesn't it? Let's think back to 1983. In 1983, your average high school teacher had a starting salary of between $16,000 and $17,000 a year. Well, 78,000 sounds really good compared to that. To be honest with you, for $78,000, I might be tempted to leave here. It's still pretty good money. Was it an honest statistic? And the answer is yeah, it was honest. It's the truth. The average really was about $78,000. But what they failed to disclose was one of their graduates that year who did graduate with a BS in marketing was a man by the name of Ralph Sampson. And Mr. Sampson was 7'4" tall and was the two-time NCAA basketball player of the year, both his junior and senior year of college. He was the NCAA basketball player of the year. He did graduate with a marketing degree, but did not go on to do marketing. He went into the NBA, was the number one overall draft choice for the Houston Rockets. Obviously signed a multi-million-dollar contract. Well, it takes a lot of $20,000 a year marketing graduates to average a multi-million-dollar contract down to $78,000 a year. Mr. Sampson was the only one in that group to make more than $33,000 that year. 78,000 was a mean. The median was around 24,000. Why the huge difference? Well, I can illustrate pretty quickly here for you. I'm going to have you guys practice here. For this set of numbers, find the mean and the median. I'll give you a minute to do this. Let's see what you got. What'd you get for the mean? 12. Median? 12. So now we're going to take that same set of numbers, and just like up here where we had that one really large number, I'm going to put another number in here. A really large number. Oh, let's see here. Let's do 78. And now calculate the mean and the median. What'd you get for the mean? Did I add something wrong? I was getting 23. 8 plus 11 plus 12 plus 15 plus 24 plus 78. No, you're right, 24.66. I had something wrong. 24.67. How about the median? So between 12 and 15. So 12 plus 15 is 27. Divided by 2 is 13.5. So you can see the median only went from 12 up to 13.5. The mean went from 12 all the way up to 24.67. This is called stability. The median is more stable. One really large number or really small number won't change the median near as much as the mean. If this were a more advanced course, we'd talk about something called outliers a little bit more. For our purposes, outliers are just numbers that are way larger or way smaller than other numbers. So stability is resistance to those outliers. You can see that one outlier, this is considered an outlier because it's way away from the other numbers. Change the mean a lot, but not the median so much. Let's talk about measures of center. Or sorry, measures of spread. So I'm going to come up with a different set of numbers here that work a little easier for us. So just a small little set of 5 numbers that we're going to use. For measures of spread, first measure of spread we're going to talk about is something called the range. Now we did the mid-range up above. The range is very similar to it. Instead of adding them together and dividing by 2, we simply subtract them. The range is the max minus the min, the largest minus the smallest. So what's the largest number in that set? Looks like the 18, right? What's the smallest number? 7. So 18 minus 7 is 11. The problem is I could come up with several other sets of numbers that also could have a range of 11. For example, I might do something like this. Oops. Let's do 7, 18, 11, 14, 13, and 11. Looking at that set, you might wonder, well, doesn't seem a whole lot different, but what's the range of that set? Well, what's our largest number? 18, smallest number? 7. So the range is still 11. But if I were trying to argue how spread out they were, I would say they're not the same. So let's do 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we'll go to there. This top set I'm going to do in red. So I've got a 9, 18, 7, 16, and 10. Those are relatively spread out. This bottom set I'm going to do in brown. I've got a 7, an 18, an 11, an 11, and a 13. I would say those are less spread out. At least there's more points kind of in the middle, isn't there? So the spread is not the same in these two, even though the range is the same. So we need to do something a little bit more precise to distinguish between them. Precision is the ability to distinguish between things that are similar. And that's what we need here, is more precision of some sort. To do that, we're going to use something called the standard deviation. Now, the standard deviation has 6 steps. There is a formula given in your textbook. I'm not going to write out the formula because the formula is very long and confusing and scary. And really, most people can't read the formula anyway, so I'm just going to give you the steps. Now, every step has a name. And it's very important that you know the name of each step, because in your homework, it'll ask you, find the deviations. Well, the deviation is just the result of step 2 of this process. And I'll give you those names as we go through this. So step 1 in our process is to find the mean. So let's use that top data set. So 9, 18, 7, 16, 10. The mean, how do we find the mean? We add them up. 9 plus 18 is 27, plus 7 is 34, plus 16 is 50, plus 10 is 60. 60 over 5 is 12. 12 is our mean. Step 2. Subtract the mean from each number. So we've got 9, 18, 7, 16, and 10. We're going to subtract our mean from each of those. So 9 minus 12 is -3. 18 minus 12 is 6. 7 minus 12 is -5. 16 minus 12 is 4. 10 minus 12 is a -2. The numbers we just found here are called the deviations. So if in the homework it asks you to find the deviations, that's what it's looking for. Step 3 is asking you to square each deviation. So -3 squared. Now here's where you gotta be careful on your calculator. You need to make sure you use parentheses or it might spit out -9. It is not. Any number squared is positive. -3 squared is +9. 6 squared is 36. -5 squared is 25. 4 squared is 16. -2 squared is 4. These numbers are referred to as the squared deviations. Step 4 is to find the sum. A sum is just a total. We add those all up. We get 90. That number there, real creative answer, sum of the squared deviations. Now, step 5 is the tricky step. Step 5, to divide by n minus 1. For this set, what's n equal? How many numbers are in that set? There were 5 of them, right? N equals 5. So n minus 1 equals 5 minus 1, or 4. So we're going to divide by 4. Dividing by 4 gives us 22.5. That number right there, this is a big one, is called the variance. I guarantee you at least once or twice in the homework, you'll be asked to find the variance. Finally, step 6, the last step in the process of finding a standard deviation is to take the square root. So square root of 22.5 4.74. That is our standard deviation. Well, let's just practice. Let's repeat this process for that second data set. Compare it to the 4.74. What's step 1? We're going to find the mean. So 7 plus 18 is 25, plus 11 is 36, plus 13 is 49, plus 11 is 60. 60 over 5 is still 12. So we still got a mean of 12. What's step 2? Subtract the mean from each number. So we're going to subtract. 7 minus 12 is negative 5. 18 minus 12 is 6. 11 minus 12 is negative 1. 13 minus 12 is positive 1. 11 minus 12 is negative 1 again. What are those called? Those are the deviations. Step 3. Square them. So negative 5 squared is 25. 6 squared is 36. Negative 1 squared is 1. 1 squared is 1. Negative 1 squared is 1. What are those called? Those are the squared deviations. Step 4 is the sum. Add those all up. We've got 64. That would be the sum of the squared deviations. Step 5 is the tricky one. You guys got to tell me this one. What's step 5? Divide by what? Not quite. Divide by n minus 1. So there's going to be, 5 is n, so we divide by 4. 64 divided by 4 is 16. That is the variance. Find the standard deviation. We have to do one more step. Square root of 16 is 4. That's our standard deviation. That is smaller than the number we had in that last problem. So that seems to support that idea that that is less spread out. Any questions? Well, there's a new quiz due tomorrow for Tuesday at the normal 11:59 p.m. There's new homework due for Wednesday. Wednesday and Thursday, we'll be wrapping up the statistics stuff. Next Monday is your Unit 4 test. We'll use the long class for the test this time just because the way it works out. Then to finish off next week Wednesday is your semester test. Then Thursday I leave open so that if you need time to do any corrections on your Unit 4 test, you've got that time to work on them in class if we have to. Any questions?